Welcome everyone. Today we are going to explore one of the most important algorithms in computer science, Dijkstra's algorithm, created by Dutch computer scientist Dijkstra in 1956. This algorithm solves a fundamental problem: finding the shortest path between nodes in a graph. Thinking about Google Maps, finding about the fastest route to the internet routers, determining the most efficient path for data packets. Dijkstra algorithm is often at work behind the scenes. Like, imagine you are trying to get from your home to a workplace. You have multiple routes available. Some are shorter but have traffic lights, and other are longer but have highways. Dijkstra's algorithm help us to find the optimal path to these all factors. So today our key objectives are understand what Dijkstra algorithm does, learn how it works step by step, see real world applications and understand its limitations. So why we need Dijkstra's algorithms? Before we dive into the algorithm, let's understand why we need it. In a network or dataset, there are different ways to measure the best path. Some might look for the path with the fewest number of connections or hops, but in real life, we often care about the total distance, time or cost, not just the number of texts. This is why the Dijkstra science, it doesn't just count connections, it adds up the weights or cost of each connection to find the truly optimal path for the criteria. So Dijkstra algorithm uses in applications like GPS navigation, network routing, logistics and delivery, social network analysis, and game AI pathfinding. So firstly, we'll talk about the graph theory. So in here, I have driven the graph of algorithm. So to understand Dijkstra's algorithm, we need to understand the graph terminology. A graph consists of nodes. These are the nodes, like the A, B, C. This should be D. These are the nodes. Nodes are the points or the locations in our navigation. Example, these could be the intersections, cities or landmarks. And the edges, these are the edges. Edges are the connection between nodes. In our map, these represents roads or pathways. And these are the edge weights. Each edge has a weight. There shouldn't be a edge without weights. A number that represent the distance or the cost or the time or any metric. This weight tells how expensive it's going to travel to that edge. All the edge weights must be non-negative. This is a must point. All the edge should be non-negative. We'll discuss in the further more, because non-negative values should be in there. No negative values can be in the edge weights. Distance table concept. So I have drawn a distance table. So this is the distance table. This is like a table we are going to understand the shortest path for the each edge or the each node. At the heart of the Dijkstra's algorithm is a simple but powerful data structure. The distance table. This table keeps track of the shortest known distance from our starting point to every other node. Like here, I have drawn the A node, the starting node. From A node to the A node, the distance is 0 because we are not traveling anywhere. A to A is 0 because from A point to A point, we are not traveling anywhere, we are still here, and the distance is 0. We visited? No, because still we are not visited, but we are in the same position. D, when we are not visited to that distance, we are marking that distance as an infinity. We are not putting any value, we are marking it as infinity, but we haven't visited it. We are marking it for the calculations as infinity. All the other nodes are same. Only A is the thing we are here, and this is why that the distance from start is 0. Initialization line. The start node gets 0 because we are already, as I said, all the other nodes get infinity, meaning we haven't found the path yet, but we know the paths that we should go with around the nodes. And initially no nodes have been visited yet, because that's why we have put a no in the visited column. And now we are thinking why we are using infinity, because any real path will be find shorter than the infinity. This ensures our discovered path will always be accepted as an improvement. There is a small calculation to find the distance from start. In there, the infinity mark will be so much helpful. So that's why we are putting it. Nextly, the core algorithm mechanism. This is the formula to do the sum. The entire logic boils down in this formula, because we'll do simple example, and then you will understand this. So if I get the current node as A, so my current node will be A, and the distance is 0 because we are still there. Next, we are going to B, to the edge B. So the edge weight will be get as 3. So weight is 3. So the calculation. New distance. We are going to find the distance between the current node, that is A node, to the node B, that the distance, that the edge weight is 3. Now we are going to find the distance. So we are going to do the calculation as the calculation will be the initial node distance is 0, then 0, and we have to add the edge weight. 0 plus 3 equals 3. Now the infinity mark is coming. If 3 is smaller than infinity, then it will be okay. If 3 is smaller than infinity, then we can update it as the distance to B. So like that we are doing the calculation. We are adding the current node distance and the edge weight, then we can get the distance to the node, or the node you want to be visited. So there are steps to do this. First, we have to initialize. What is being initialized? Like set the star's distance to 0 and all the others to 0. As I said earlier, your source path, your source node should be 0 and all the others should be infinity. And select what you are going to visit. Pick always the unvisited node. If you have visited to a node B, if you are like, let's get this example. If you have visited to node B, then you can proceed like draw a cross or a line like this and remove it. Then you can't revisit this node. Then you can go to A to C like that. And thirdly is visit. Mark the node as visited, like I said earlier, cross or do something to memorize that you have visited that node. For each neighbor of current node, calculate current distance. All the nodes should be calculated like that in the calculation. And compare what is the shortest or the smallest distance you can go. So repeat until all the nodes. You can repeat. You have to repeat this as the all nodes are being visited. Importantly, we always pick the closest unvisited node. Like now I have visited to A to B3 and the closest is C to D. Like that. But you can visit to C to D directly. Then you have to go to A to C. This works because with non-negative weights, the shortest path to any node won't go through a node that's farther away first, like this. So we'll do example, we'll do calculations, and we'll find the shortest distance. Now I have drawn a graph like this. There are 5 nodes A, B, C, D and E. And I have drawn the table concept. I have initially my initial node is A and the distance from start is 0. I doesn't still visited it and these all are infinity because I haven't visited it yet. So the first process A. A is the closest to 0 line. This is 0. So mark it is like I'll drawing a cross so I can memorize it as I visited. So A to B 4. Then I'll do the calculations here like okay. A to B A to B A to B we'll find the calculation. Initial distance is 0 and here we are visiting to the node B, then the weight is 4. Now we can find the answer, that is 4. Okay. A to C. A to C equal 0 plus 2. So we are getting the answer as 2. Now we are going to the step 2. C is the next closest, like 2. 2 is the edge weight. So we can mark as visited. Okay. Now we are going to do the calculations. Okay. C to B, we will find the distance C to B. So C to B goes 2 plus 1. Then the distance is coming as 3. 3 is smaller than 4. Now this is the crucial point. Okay, the distance is, initially we got it as 4 in here, but now the distance is coming to 3. So we can update the in here. Okay, this is from the second step we get the distance as 4, but now we can find that the 3 is the smallest part. Then we can update 3 as the distance for B, because it's the smallest. We are getting the smallest part. If we got like 6 in here, we don't update 6 in here because 4 is smaller than the 6. We'll continue, and C to D, we'll find C to D. C to D, 2 plus 8 comes 10. So D is 10. I find that also. We will find C to E. C to E is 2 plus 10, getting the distance as 2a. Now we can update E as 2a. Okay, so we have visited B as 3, C only visited, D as 10, E as 2a. So next process, like process B is 3, mark visited. Then now we have visited B. So we can find B to D, because still we didn't find B to D. Okay, now we will find B to D is, initial distance is 3, because we have find that distance to B is 3. Now the initial distance is not 0, 3. 3 plus 5. So now the distance is smaller. That value we find initial. Now we have to update. We are erasing the 10 and we are updating the new distance as 8, because we always get the shortest distance. So we find B to E. B to E is 8 plus 2, 10. Now also sorry, wait a minute. Sorry. So B to E already 12, no better path where B. Okay, now we can go to the process D. D is the next mark. Then we can mark that as visited. So D to E, we are going to find D to E. Eight plus 2, 10 is smaller than 12. We have to update. So E is the last, and we have find that E. We are going to write the final results. We write the final results. A to A is 0 because the initial distance. A to C is A to C to B. We find A to C to B is 3. We are find them. So next A to C. So A to C is 2. In here we have find that A to C is 2. So we can now find A, C, B, D. So distance is 8. Now find that. Is 10. So these are the final distance. A to A is 0, A to C to B is 3, A to C is 2, A to C, A to C to B, A to D and B to D is 8, and A to B, A to C, A to D and A to E is 10. This is how we are doing a calculation in Dijkstra's algorithm. So we are, as I talked earlier, we can't add negative weights to the edge weights. So we'll talk about that. The algorithm assumes that one node is visited. We have find the shortest path like in this calculation. With negative weights, this assumption breaks like that. If you get minus 1 plus 3, then it's always getting the minus value. So like we visit to A and we update B to 5 like with a distance value. So we see B 5. We can update C to like minus 3 5 plus 8. It then makes minus 3. But what about the direct A to C path of 10? It's no longer. Like so Dijkstra wouldn't be reconsidered. So real world applications like as I said earlier, despite the negative weight limitation, Dijkstra's algorithm is incredibly useful in practice like GPS navigation, network routing. In GPS navigation, like every time you ask for the faster route, not for the slowest route. Network routing, especially like internet protocols use like these algorithms, social networks finding the closest connection between people, like in telecommunications also routing phone calls efficiently. So at last we have like Dijkstra algorithm teaches us like the shortest path. We are getting the shortest path. So this is the end, and I'm going to conclude this video. Thank you.